Hey there, AP Stats students. We have another video for you. We are going to take notes on section 10.2, specifically the 2 sample t interval from section 10.2. And I wanted to actually show you all the things that I have to take my notes, and I think you should get all of these things too. First, I have my calculator. I really think you should be typing in numbers along with me and making sure that you're putting them into the formula correctly. Too often in class, you guys are getting wrong numbers, and it's literally just typing numbers into the calculator wrong. So if you type along with me and get the wrong answer, you can ask me about it in class, or Miss Milsick. I also have my formula sheet because I want to point out that this formula is going to be used for difference of means. So we just want to make a little note on it and say that's the one we're going to be using. So why don't you gather all those things so we can get started. All right, so what is the purpose of a 2 sample t interval? Well, we've already done a 2 proportion z interval, so it's going to have the same purpose. It's just going to be about means instead of proportions. I don't know why the title is a 2 sample and not a 2 mean, but that's just the way they call it. So it's going to be to use 2 sample means to estimate the difference between 2 population means. So this idea of using an interval to see the difference between 2 groups is not anything new. We just did it with a 2 proportion z interval, which was your yellow template. But we also did this back in chapter 8. So way back in chapter 8, we looked at the difference between 2 groups, but we did paired groups. And so the big difference here is that they are not paired groups. The example that we did, I think, was the one with the bean placement thing that we did. So you guys either used your dominant hand or your non-dominant hand to place beans on a target, and we counted up how many you were able to do in 30 seconds. And because everybody participated in that and they tried both treatments, both with your dominant and non-dominant, the data that you had from your 2 groups were paired up. And so we instantly subtracted them and made them into a 1 sample. Well, now what we want to do is, what if they're not paired up? What if instead they come from 2 different groups, or it's an experiment that's not a match pairs, it's like a completely randomized design and you just have 2 separate groups? How would you analyze that data? Well, when they're not paired and they are 2 separate groups, there's nothing that's going to take them and put the numbers together to subtract. So instead, we're going to have a new procedure. That's what we're doing today. So our example is about the Pac-Man data. Some of you got to actually participate on this in class, where Miss Meadows and Miss Milsick are trying to determine whether playing Pac-Man with sound or playing Pac-Man without sound would make a difference in your score. So we let some of you play Pac-Man, just one life of Pac-Man, either with sound or without sound. We randomly assigned you to one or the other, and then saw how far you got with one Pac-Man life. So I've been collecting data for a long time now, and I've actually got tons of students. I've had 60 students play with sound, 64 students play without sound, and you can see the average score with sound is actually lower than the average score without sound. Kind of shocking to me. But there's a massively huge standard deviation. My scores have been kind of all over the place, if you're interested. I really have been collecting data for years. Look at all this data. So I've got someone got 160 points with 1 Pac-Man life, and then 350 or 3,580. So they're kind of all over the place. So I have a really, really, really big standard deviation. So what we're trying to just see is if we can see how many points on average would you expect to be the difference between the 2 of them. We're going to do a 90% confidence interval to estimate the difference in the mean scores to see how much bigger the difference is. So let's start with our assumptions and conditions. We're going to jump back into the means assumption and conditions, but independence doesn't really change. We still need to have a random sample or random assignment. Since this is an experiment Miss Meadows has been doing, I've been randomly assigning every single kid that plays it to either sound or no sound, so put a check on that. You can lump all of them together when it's an experiment and not do two separate 10% checks. So far 124 students have done it. That's less than 10% of people. And then finally, because I didn't pair them up in any way, which I could have done, I didn't do that though. I could have had one person randomly do sound or no sound first and then play again with the other way. I chose to do it as a completely randomized. You only were in either the sound or no sound groups. So that means we have two independent groups. So that's just like what we said in two proportion. The same idea is true here. We want to make sure the groups are not linked or paired in any way. The next is, remember we have multiple choices. Either they tell you the population is normal, which I did not, or it's large enough, which it is. And we have two large enoughs now because we have two samples. So the 60 is greater than or equal to 30, and the 64 is also greater than or equal to 30. So that's so easy. We love it when we have large samples. Stay tuned for in class when I'll give you one where you'll have to make graphs, and you will have to make two graphs to check for normality if you have less than 30 pieces of data for either of your groups. Okay, and then you will say, I will create a two sample t interval. So this is actually our fourth confidence interval that we've done. And they all follow the same exact structure. This is actually written on the formula sheet. I shall show you. It says right here that all confidence intervals are statistic plus or minus critical value times the standard deviation of the statistic. So we are going to have that same kind of idea, except for our statistic is no longer going to be a single x bar. It's going to be the difference between two x bars. Our critical value is still going to be a t star whenever we're using means, and we'll talk about degrees of freedom in a second. And then we have a brand new standard deviation, or actually standard error. It's sort of on your formula sheet, but I want to show you where it came from. So sidebar for just a second, you can just watch. This was the old standard error for one sample. It's just s over the square root of n. But now that we have two, so we got two s's and two n's, how are we going to combine these two standard errors? So it's going to be like what we said with proportions when I sidebarred in our first video. You're going to square each one of these, add them, and then take the square root. So let's simplify this a little bit. S1 squared is just S1 squared. But this square root of N1 and the square will cancel out and just become N1. And then same thing over here. S2 needs to be squared over N2, and then a giant radical. So this is going to be our new standard error. It's a combining of the two previous ones. And they sort of put this on the formula sheet, so why don't you grab your formula sheet. They say difference of sample means is the statistic we're looking at, and that is what we're looking at, x bar 1 minus x bar 2. And you see the standard deviation of it is right here. They use sigmas instead of s's, so you just need to remember to change those to s's. But this is going to be used for our standard error. And you'll find out it's for the interval and the test, but we're not going to do the test until next class. This one you can even cross out. We're not going to use that one. So not much that needs to be memorized. Let me zoom in. Oh, sorry, I can't zoom in. Just take a look that I put s's here instead of sigmas so that it matches this formula. All right, so let's write that down in our notes. The new standard error formula is S1 squared over N1 plus S2 squared over N2. All right, so pretty much everything is given up here. There's 1, 2, 3, 4, 5, 6, 7 numbers, and I have 6 of the 7 numbers up here. The only thing left is the T star, so this sidebar I definitely want you to write down, is how do we get degrees of freedom? So we can look it up in our chart. Degrees of freedom is usually n minus 1, but we have two n's, so what do we do with that? This n is going to be the smallest of the two n's. That is going to be making sure that we have a big enough T star so that we have an appropriate margin of error. So we want to use the smallest, so in this case our degrees of freedom is going to be 60 minus 1 or 59. And that's what we'll need to look up our T star. Well, here's a problem. If you could grab your chart real quick. We want to be 90% confident, so that's fine, but we don't have 59 on the list. So you can just use 60, or if you want to use 50 to be really, really safe, it doesn't really matter. You can see the difference is like 5/10,000th of a decimal, so not a big deal. I'm just going to use the 1.671, which is the 6490. Okay, 1.671 is what we're going to use. All right, so we're going to go up to the top now. Here's one thing that you get to choose. The subtraction matters. If you want to just do it in the order in which I presented it to you, then you would actually get a negative difference. That's completely fine, but I like to keep my sample difference positive. So I'm going to put the sound first. So I'm going to let 1 be sound and let 2 be no sound. And I'm going to do the 2,333.28 first, minus 2154.2 for the no sound. And then plus or minus, my T star is 1.671. This big giant square root is using my S's. Now this doesn't matter because you're going to add them, so I'll just do it in order though. 1816.25 squared over 64, that's for my no sound group, plus 1363.2 squared over my 60. So just use the numbers that were given to me. Real simple. All right, calculator time. Let's do the stat first. 2,333.28 minus 2,154.25. So we got, or Miss Meadows has gotten, a difference of almost 180 points for the no sound actually getting a higher score than the sound. But we know that we can't just say, okay, if you don't play with sound, on average you're going to get 180 points more playing Pac-Man. Nope, we have to give it plus or minus, like how much off is that going to be. So as we've talked about in the past, if you do this whole thing, it's margin of error. If you just do the square root, that's standard error. I'm going to do the whole thing. Can we see it? Speed up a little bit. 1.671 times the square root of 1816.25 squared over 64. So I'm just typing straight across everything I see, plus 1363.2 squared divided by 60. And we press enter. We say plus or minus 480 points. Oh no, what that means is that our margin of error is saying we are expecting to be off by about 480 points, and we only average a difference of 180 points. So that means I'm going to go into the negative. So 179 minus 480 is negative 301. And then if we go up and add the 480, we get 659. So that's actually not very exciting. We were hoping to prove that one way or the other was the better way to play, but because the interval goes from negative to positive, it's what we call inconclusive. A negative difference would actually mean that the no sound group was higher than the sound group. A positive difference, like we got in our sample, I'm sorry, I said that backwards for the first one. I'm sorry. A negative difference means that the sound group would be higher. I wrote this wrong from the beginning. Oh my goodness. Sorry. No sound was 1, sound was 2. So if we get a negative difference, it means the sound is higher. If we get a positive difference, it means no sound is higher, since we put that first. And 0 is also in there. So it's quite possible sound has no effect at all on the average Pac-Man score. So it's not very exciting. We're going to write, I am 90% confident that the average difference in Pac-Man scores with sound and without sound is between negative 301 points and 659 points. You could have also said I'm 90% confident that the average Pac-Man score with sound is between negative 301 and positive 659 points more than the average score without sound. But I find that awkward when it's a negative positive because you're saying negative and more, so that gets a little confusing. So this is kind of a generic sentence about trying to figure out the true average difference. All right, let's flip over to the back. Oh, oops, we already did this. C front. The interpretation of the interval is just, I am 90% confident. So we already did that. But what does 90% confidence mean? This is something that we've struggled with back in chapter 8, so let's practice. It means if many samples were taken, then 90% of confidence intervals created will capture the true mean difference in Pac-Man scores with sound on versus no sound. Okay, real simple. Didn't talk about my interval, just talked about we're hoping our interval is one of the 90% that capture the true mean difference. Margin of error is just, we already calculated that as the part after the plus or minus, but I also like to remind you that margin of error is half of the width. Oops. So the interval spans from negative 301 to positive 659. So one thing you can do to find the width is add the ends, and, I'm sorry, not add the ends, that's averaging. Subtract them and divide by 2. That would be your margin of error. So careful there, you're subtracting a negative. So 659 plus 301 divided, enter, divide by 2. So we already knew that our margin of error was 480. Just another way to calculate it if I have the interval first. And then finally, do we have conclusive evidence of a difference in mean Pac-Man scores? And the answer is no. The interval includes negative, positive, and 0 options for the true mean difference. In Pac-Man scores. It is plausible there is no difference with and without sound. All right, we already talked about that, so that's just a way of saying it. You could set it different ways. All right, guys, see you in class.